Okay, welcome to Quantum Field Theory, lecture 14, I think. So we are moving fast. 14, that's a lot. 14 weeks. Wow. Uh, we are trucking along the scattering amplitude journey. Right now, we're seeing that there's a lot of intuitive things we can take away. And kind of we're seeing that the mathematical structure of these scattering amplitudes is pretty impressive, pretty phenomenal. But now we kind of want to push it and see how far we can take it, right? Because we've only been working at tree level, and we're going to be working at tree level today and next week. I'm not going to loop level. But is there a way, and this should be the overarching question, which I'm not going to really answer fully today. I'm going to answer fully next week, but we'll start getting there. You should ask yourself, the question of the puzzle really is there a way to somehow write down higher point amplitudes or all point amplitudes in a simplified form? And you should have the inkling that yes, there is, because then what would be the point of this? But how do we get there? That might be a little bit of a puzzle, and that should be the big overarching question. Remind me where we left off last time, so I know. And then we'll get started.
You just briefly introduced Yang-Mills.
Okay, but I didn't show you any gluon amplitudes, right?
I don't think so.
Okay, so then let's just start right from the top of Yang-Mills again. Okay, so let's just start with pure Yang-Mills theory, or when people refer to gauge theory, they're referring to Yang-Mills theory, just gauge theory in general. Okay, so we should start with the Lagrangian. So I'm just going to write down the gauge fixed Lagrangian, skip all of that. Because remember, the standard Lagrangian is trace f mu nu, right? But you have to gauge fix that by a covariant derivative. So, right, so let's just trace. No, wait. I want to make sure I get this right. Right, that's trace minus 1/2 d mu a mu d mu a nu. And you're going to start seeing all of these extra terms because of the gauge fixing. So don't be scared of that. Minus I square root of 2g d mu a nu a mu a nu. Plus g squared over 4 a mu a nu a mu a nu. Right, that should be the gauge fixed Lagrangian. Okay, so this is just regular gauge theory, nothing really spectacular. Okay, and one can derive a Feynman propagator from this that goes delta AB, where AB is the color index, eta mu nu over p squared. Okay, so this is what the Feynman propagator looks like in gauge theory, pure gauge theory. This is just this should look very familiar, right? Because this just has the standard p squared pole, eta mu nu from the fermion stuff. And all I'm doing is adding this little guy to keep track of color, delta AB. Okay, and then we know that the 3 and 4, when we have n equals 3 or 4 gluons, well, then we know we're going to get some color factors or group theory factors, right? So like F tilde ABC. And then for the 4 gluon, we're going to get like some ABX, F tilde XCD, right? And these are just the group structure constants, right? That come from the group, the SU3 structure of Yang-Mills. If this is at all confusing, I think Lancaster Blundell touch on all of this in that chapter in Yang-Mills theory. Okay, so this is just from the group theory structure. Okay, very good. Right, because this comes from that Lie algebra, right? TA, TB equals I, FABC, TC, right? This is the whole algebra of Yang-Mills theory, where T are the generators. Okay, I think I remember now. I was at the Jacobi identity, right? I didn't actually write it down for you, right? Okay, good. So let's write down the Jacobi identity. So we have a CS, we'll call this CS, and you guys should be somewhat familiar with this. This is just, so I'll call this F tilde A1, A2, B, F tilde B, A3, A4. So this will be the group theory factor for the S channel diagram. We'll just say. It doesn't have to be, so this is defined as, but it doesn't have to be. And now basically all I'm going to do for the other two channels is write down permutations of these group theory factors. So I'll write down a permutation A1, A3B, F tilde B, A4, A1, A2. Okay, that's a permutation. And now I need one more permutation. So CU defined as, well, what's the last permutation that I need? I exchanged 2 and 4. Now I need one more permutation. What can I do? 1, 4, yeah, let's do A1, A4, B, B, A2, A3. Okay, that should be it. And the Jacobi identity, I think that's right, yeah. The Jacobi identity simply says that CT plus CU plus CS is 0. Jacobi ID, okay? Which anyone who's looked into this has seen this, right? Seen this idea. Or you've seen this just from Yang-Mills theory. Everyone writes this down because the goal is to get rid of these guys, right? They're just kind of like there as extra baggage. Okay, can I erase the board? Okay, so that's just sort of the basics of Yang-Mills theory. And actually, I don't know if you've looked into this. At tree level, Yang-Mills is fine. We're working at tree level. At loop level in Yang-Mills theory, you get these things called ghosts. Okay, so for those of you that want to look into that, you get these things called ghosts. You get extra degrees of freedom that aren't there. Kind of interesting. Okay, there's another very important identity. So I can write down these group theory factors. So I can write down this group theory factor in a very nice way. I can write it as permutations of traces of the group generators. Okay, what do I mean by that? So I can write it as permutations of the T's in my Lie algebra. Okay, so I can write this as trace. Wait, can I or can't I? Right. Trace TA, TB, TC minus trace TB, TA, TC. Just doing a permutation. Okay, so that's another way I can write this guy. And we also have the identity that I can write down the group generators in this way, TA, IJ. There's another identity. If I take the product of two of the same group generators, then I have this guy, KL. Equals delta IJ delta KL. So you get two Kronecker deltas, and you can verify this if you just look up what the group generators are. minus 1 over n. N is the number of particles. Delta ij, delta ki. Okay. Any quantum field theory textbook on Yang-Mills will tell you all of this. This is not really anything very fancy. Okay, now before I write down a Yang-Mills amplitude, I kind of want to backpedal. I forgot to show you one thing last week during QED, which I should have shown you. It's just another identity, right? Spoiler. It's actually called the Schouten identity. It's the reason it's very important because we use it a lot to simplify stuff. So you can verify all of these as usual. So what is the Schouten identity? I'm just going to show you this because we use it a lot. So it's just this little product. So I, JK bracket. And again, shouldn't be any surprise that the permutations will add up to 0. So J, I plus K. I did Ki and I have Ij. Okay, so that's just a Schouten identity. That's just this is totally unrelated, but I remember that I never showed this to you. And then when I say, okay, we're going to shout in this amplitude, like, what is this guy talking about? So that's what I'm talking about. Okay, very good. Okay, now we can write down some Yang-Mills amplitudes. And they're going to look kind of crazy, but just bear with me because I'm going to use some of these rules or some of these properties. Okay, let me know when I can erase. Okay, very good. By the way, I just want to say, in any paper you look at, any paper that explores these modern techniques, they're usually going to look at gauge theory before they look at gravity. Okay, that's what people do. You work out the gauge theory case, and then you work out the gravity case. So it's very important to know Yang-Mills theory well. The thing is that's not really taught too much in QFT classes, but there's plenty of stuff out there to read about it. So it's not very. Okay, so let's write down a 4-gluon S-channel diagram. Okay. And I'm not going to specify anything. I'm just going to write down just the basic schematic. So if I had a 4-gluon S-channel diagram, I know I'm going to get some group theory factors, F tilde A2, A1, A2B, F tilde B, A3, A4. Okay, I'm just writing down the group theory factors. And I know that this guy is going to be proportional to what? It's going to be proportional to all of those permutations of the generators, right? Based on the identity I just wrote down, right? So I'm going to get some factor that looks like, I don't know. This is going to be kind of nasty, but we have to do it. Trace TA1, TA2, TA3, TA4. Someone want to give me a permutation? What's one thing we can do? I mean, does everyone know what I mean by permutation, or is that unclear? It's okay if it is. I'm just exchanging these and then, just flipping them around. So one thing I can do just right away is flip the 3 and the 4, right? Okay, so let's do that. Okay, so T, A1, TA2, TA4, TA3, right? We're going to need we're going to need all of them. And we know there's going to be 4 of them because there's 4 objects here. I don't know, trace of T, let's do A1, A3, A4, A2. And now the final one is just going to be what? What's the final guy going to be if I set it up like that? Right, it's just going to be TA1, TA4, TA3, TA2, I'm pretty sure. Yeah, that looks good to me. Okay, so this is fine. This is the group theory factor, right? These are the structure constants. I haven't really done anything crazy. I've just taken the identity and written it out for a 4. So this is just an n equals 4 S channel. So S chan. Gluon. N. Right? Why is it S channel? Look at the structure of the group theory factors and match it up, right? I would have a T channel process. I would have a U, everything. See, this is kind of, it's crazy, right? Because you're just relabeling a lot of the times. So just, it's not really too deep. Okay, so let's write down the schematic of the full amplitude, right? Because this is just the little group theory factor we need to add in, right? This just comes in. If you read any textbook on the Feynman rules for Yang-Mills, you find that these guys are everywhere. These little group theory factors come up everywhere in all the amplitudes. So I just wanted to work out just how that looks explicitly. So now if I write down A for full, we'll call this full at tree level. I promise we'll do loops eventually. It just like loops just add a lot of complication. Okay, and we're going to have a coupling G squared, right? Because there's 4 particles. So your coupling is going to be to order, squared when you have 2 vertices. We're going to have some amplitude that's made up of these angles and spinors. We'll just call this A4, 1, 2, 3, 4 for now. Right, so this is generic for some angle and bracket thing. And then we have this extra guy, which we just found. So this is just TA1, trace of TA2, TA3, TA4, and then plus all permutations. Well, that perms. Not the hairdo. Okay, so this is the schematic. This guy obviously depends on your helicities, right? Whether it's vanishing or non-vanishing. And gluons can have helicity of what? +1 or -1, right? This guy is what we just wrote down. This is kind of the extra junk, okay? So these have a special name, okay? These guys. They're called, so first of all, these are partial amplitudes, right? If I just look at this term alone, in the case of Yang-Mills, because we don't have this whole group theory term. So in Yang-Mills, these guys are called color ordered amps. Color ordered. Okay, or some people refer to them in the literature as just partial amplitudes. You'll see that sometimes. And then when people write them as partial, and we're going to work out a real example, don't worry. It's very funny to me. I was working with Monica the other day, and she goes, yeah, in America, we learn by examples. In Europe, they just do the general case. I was like, actually, Feynman had a very famous quote, right? That said he always learns by examples. He actually discussed his process, that the general case was never really, this is not the general case, obviously, because this is n equals 4, right? I'm going to write down the general case. In general cases for any number of particles, you should be able to write down an expression. But that's funny, just the style. So we will work out, and we always work out examples here. So I just thought that was interesting, the contrast. Okay, let's write down the general case. Okay, let's write down the general expression. Now, sort of ominous after I make that point, but we should write it down. It's pretty easy actually in this case. Not really a big deal. So that was for n equals 4, and that was just the brief like schematic, right? I didn't really work out the amplitude because that little A4, 1, 2, 3, 4 has a lot of stuff in it, right? Angles and boxes and all of that. That's a given. Okay, so then AN full tree. So the endpoint amplitude now is just going to give you some Gn minus 2, right? Because the vertices will always be 2 fewer than the number of particles. That's something you can actually prove, right? We'll write this just the sum of all permutations. Okay. So we'll call this perms of sigma. We'll see why in a second. Right, and then I have AN 1, so the first particle, times sigma from 2 to n, right? Because the S channel is going to switch them, the U channel is going to switch them, all the channels are just going to permute the particles, right? And the signs and all of that. So I just encoded that in that. And then, of course, we have to have our little group theory guy. So trace of TA, TA1, T sigma, A2, TAN. That's it. I mean, so this case generalizing is really simple, right? It's just easy, right? You just keep permuting and you just get all of the amplitudes, all of the terms.
After the square bracket on the first line, does that say A4?
Oh, no, sorry. That's from last.
Oh, okay.
Yeah, sorry. I didn't erase. Okay, I'm also going to write down, so of course the vertex doesn't just have a coupling. There's a little bit more to it, right, than just n minus 2. Right, so g to the n minus 2, if I have right, so this just tells you this is something you can show that this is you get g to the n minus 2 for any n number of particles. Right, yeah. I'm just thinking if that factor's right. No, it seems right. Right, because look, if n equals 4, 4 minus 2 is 2 g squared, right? We just worked that out. Okay, so let's write down the 3 gluon and 4 gluon vertices. So this is the 3 gluon vertex factor. So this is just, again, something you should have seen if you've read about Yang-Mills. So I'm not going to go too into it. And we just write it down as like some v mu1, mu2, mu3 of p1, p2, p3. It's just some vertex factor. Okay. Oh God, how does this go again? Right, so minus square root of 2. It's just going to be a bunch of etas, but I just want to remember how it comes out. Right, eta, u1, u2, p mu3. P1, obviously, plus eta, I don't know. Is it the same? Can I do the same thing? No, I have to permute. Mu2, mu3, p2, mu1. Right? It's eta mu3, mu1, p3, mu2. Okay, that's the 3 vertex vector. Okay, and the 4 vertex factor is more annoying. I'm not gonna write it down. You just get a bunch of junk. That's it. Okay, shall we work out a color ordered amplitude now? So color ordered being the amplitude without all the group theory stuff for gluons. Okay, let's do it. So let's work out a colored ordered amplitude now in detail. Because the group theory stuff is pretty straightforward. It's the same from just normal quantum field theory. But this color ordered stuff is what we're going to write down in the spinor helicity formalism. Okay, so I hope you're somewhat familiar with Feynman amplitudes in Yang-Mills. If you're not, this is gonna not make any sense, but it's okay. If you're not, then go and read about it after and then match it up, because they're very similar, obviously. Okay, so let's just do a 3 gluon amplitude. So n equals 3. Let's just do the simplest case. Okay, n equals 3. So in the normal Feynman schematic, you would have something that looks like this, right? That's what we're trying to compute now. Partial amplitude of 3 gluons. And you'd have some minus √2, whatever, normalization out in front. And then you would have a bunch of polarization vectors dotted in with one another. So epsilon1, epsilon2, epsilon3, P1 plus, and then you'd have all those permutations. That's like what a normal gluon amplitude kind of looks like. So epsilon2, epsilon3, epsilon1, P2. I don't know, plus epsilon3, epsilon1, epsilon2, P3. This is what just a normal kind of schematic would look like. Obviously, have I specified the helicity? No, right? That's what these epsilons are going to encode, right? Okay. This is going to make sense in a second with spinor helicity, but you see, this comes right out of normal Feynman rules for gluons. It's like this is a very easy kind of expression. Now, should we spinor helicity this up or not? It's really up to you. We should? Okay, I think we should, because we're doing spinor helicity. Okay, so let's have 1 and 2 have negative helicity, and let's let 3 have positive helicity. So this is A3, 1 minus, 2 minus, 3 plus. And you should already be going, oh no, something fishy is going to be happening with the helicity. You're absolutely right. We're gonna get there. Let's just work out the computation for now. Then we'll talk about that. Okay, so now I need to write this in spinor helicity. Right. So let's just put a minus sign out in front. And let's not worry about the √2 for now, or forever. Okay. Right. 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 So this is going to come out as a sum of angles and squares and all of that. So it should look kind of similar to the QED stuff. I'm just trying to see how long my expression. So I'm going to get a minus. We'll get some 1, 2. Let me just think about this for a second. I have to think. Right. Q1, Q2, Q3, 1. I'm just going term by term and working it out. One, Q3 plus, we're going to get 3 of these guys, obviously. The question is, well, how do you dot everything into one another? 2 Q3 Q2 3. Forgive me if I make an error. 1 2 2 Q1. Okay, we're going to have one more term in the numerator. Q3 1 3 Q1. Uh, 2 3 3 Q2. That should give me the numerator. Now what's in the denominator? This guy. That's easy. Q1 1 Q2 2. Q 3 3 angle. That should be right. You can go back and match it up with the rules and write it down. I think that's right. Okay, if you don't see how I got this, then just go read about it. But now hopefully we can use a bunch of identities and simplify this, right? That's the plan. Can I erase this top expression? Okay. Okay, very good. And let's see. Okay, good. So this is a good interlude. So this will be your first exercise, okay? By the way, I didn't type these up. So if I forget, I'll email you to tell me what I asked you to do, and then I'll type it all up. So your first exercise will be to work this out and show, so then now we're going to work with the result. Show that if you use the Schouten identity, you use proportionality, you use all of these different things we're learning, show that this final amplitude comes out in this beautiful form, 1 2 cubed over 2 3 3 1. Okay, that's your first exercise. And this is just a 3, 1 minus, 2 minus, 3 plus. All right, because I don't have to work through all of it. I've worked through a few of them already for you. And the scattering amplitudes, obviously read the archive thing, right? That's going to help you a lot. So, because they work it out there. Okay, can I erase the bottom expression? Okay. Okay, very good, very good, very good, very good. So anyways, the point is, do you want me to work it out, or do you think you'll be able to do it? You think you'll be able to do it? Okay, good. That's the spirit. I could spend 15 minutes and do it, but I think I've done a few examples for QED, so it's good if you guys take that. Okay. Okay, so let's just now pretend we did it. We're sweating a little bit. This is kind of crazy. This is a great result. It's very simple. This is the kind of, we're still playing around with it. We don't really know if we can, because remember, I told you that you should be asking yourself the big question. Is there a simple way to write down everything? We're not there yet. We're getting there. We did a 3-point amplitude for gluons. Okay, here's another exercise. Okay, show that the 4-point amplitude, this 4-point amplitude, Which, by the way, the helicity should be a little scary to you. We're not scary. You should start having some alarm bells. Yields this 1, 2 to the 4th. So now you show me the 4-point amplitude. 1, 2, 2, 3, 3, 4, 4, 1. Okay. Notice you start to see patterns, right? You should start to see patterns. Also, the helicity should be interesting to you. We'll talk about that. Also, you see in this denominator 1, 2, 2, 3, 3, 4, 4. You see these guys are the same number. Don't we have an identity that works like that? Where you can write them out. So you see there's a lot of patterns. It's very good for people that like patterns. In fact, we can generalize this result. So you're going to finish this 3-point case. You're going to work out the 4-point case. For now, I'm going to show you the helicity craziness in a second. But at this stage, you'd be like, oh, this is weird. Why would he put, right? Why would he put now 2 positive helicity? Why did he make 4 negative? We're going to talk about that in 5 minutes. But let's write down the general case now. So for any tree level amplitude, Park and Taylor worked out an expression for any tree level gluon amplitude, and this should kind of be nice for you. So this is a very famous result in this study. So this is the Park Taylor. Okay. This is a very famous result. And so this is for N gluons. Okay. And what they showed was you can write down, and again, the helicities are going to be very, very funny to you. Okay. So you have some AN, right? Okay. You have 1 plus I minus minus plus. Okay. Equals ij to the 4. And then in the denominator, 1, 2, 2, 3, and 1. Okay. So this is the generalization, not very hard to see, right? Even just looking at the 3-point, then the 4-point amplitude, right? So this is a very famous expression in the study of scattering amplitudes. This was derived in the 90s. And this is sort of like the first big thing people started to look at. Like, this is pretty neat. Now, the thing to note is the helicity. Obviously, that's not random. So we're going to talk about that in about 5 minutes. Okay, very good. Okay, so let's do a little exercise. So let's just say we have n equals 3, 4, 5, 6, 7. And I ask you the question, okay, and we've done this before, how many tree level diagrams do we get? Okay, let's just write it down. Actually, because I actually looked it up this time. Number of diagrams at tree level. Remember, how do I get, because remember, each diagram, all that corresponds to is a different permutation of an index, right? That's why you get so many different diagrams exponentially as you go up. So here you have 1 diagram, 3 diagrams, 16 diagrams. Okay. Not so bad, okay. 38 and 154. So pretty phenomenal that we can distill all of this into one expression. Of course, in this massless limit, right? Okay. So that was actually where I wanted to end last week, right? Because remember, we had to shorten it up. So this is technically all of last week. So now we're going to start a new topic based on this stuff. Okay. Okay. Can I erase the board? Oh. Okay. So now we're going to look at another property of these guys that turns out to be very important. And actually, it's kind of this property of, so there's a few observations you should make. The first observation is what's going on with the helicities, that's fine. Second observation you should make is, wow, these things are really simple. Third option you should make is, wow, these things are really simple. What are we really looking at here, right? And actually, if you just take a step back, all you're looking at are a bunch of momentas, okay? Just doing crazy things. That's it. That's the whole name of the game. And in fact, in the massless limit, that's kind of, right? You might remember when we did high energy scattering amplitudes. That's a pretty good way to do things. So we can play games now with how we want to transform the momenta, right? That's what we do in physics, right? We see how we can transform things, right? We try to find symmetries of the objects, right? And we see what new things that those symmetries give us, right? That's what we do in physics. So let's do that. What symmetries do we have of these momenta? What can we do to these momenta that leave them invariant, that leave the amplitudes invariant? More specifically, more precisely, that leave the on-shell amplitudes invariant. Remember, these are all on-shell. It's not like normal Feynman. Normal Feynman, you go off-shell with the virtual particles. Everything here is on-shell, i.e. p squared equals 0. So let's play around with this. So recall, right? So recall that P angle and P box are solutions to the massless Weil equation, right? So these are just solutions to this guy, P 0, just the massless Weil equation that we are familiar with. Okay, and this is, of course, this is for on shell, for P squared equals 0, as I just said. Okay, and from this, remember that we wrote down this object, so PAB dot equals minus PA PB dot. So this is going to be very sort of provocative, but the first thing I can do is I can rescale all my momenta. That's something I can do. Okay, so that's what we're going to explore. So all of these relations are invariant under the following scaling. So if I let P go to some constant T times P, and I let box P go to some T minus 1 P, everything stays invariant. It's just some rescaling. And if I do that, well, then these T's just cancel each other out. Okay. This seems very trivial, but oftentimes, right, for example, Poincare symmetry, translations seem trivial, rotations seem trivial, but they give rise to Lorentz invariance, right? Okay, that's a pretty big physical thing we have to think about. So just, don't dismiss these symmetry. Oh, big deal. I scale it, whatever. Watch, we're gonna extract something interesting out of this. Okay, so what theory is based off of scale invariance? Conformal field theory. Okay, they're very interlinked, and you're gonna see how, it's kind of cool how interlinked they are. Okay, anyways. So this is called little group scaling. So this is called little group scaling. What is the little group? It's a group of transformations, right, that leave the on-shell momentum invariant. Okay. So for example, rotations in the XY plane, so rotations in the XY plane, yes, rotations in the XY plane leave P mu invariant, right? They leave the momentum invariant. So they're part of the little group, right? Any transformation that leaves the momentum invariant is part of the little group. So for example, in the XY plane rotation, the little group representation is SO2, which is isomorphic to U1. Okay, so that would be the little group representation for that transformation. More precisely, the little group is actually E2. Okay, and E2 is a group which maps rotations in the 2D plane onto itself. So you're taking all rotations in the 2D plane. That's what E2 is. Okay. What does E stand for? Look it up. Okay. That's problem 3. Look up E2 or little group rep. Why is that the little group? By the way, the guy who discovered this was someone named Eugene Wigner, you may have heard about. So if you look this up, sometimes they're referred to as Wigner's little groups. Okay. Okay, very good. Okay, so we can scale things now. Okay, that's a good little invariant thing we can do. Now you should ask yourself, okay, Kyle, wow, thank you so much. You told me something that's kind of seems trivial. But now you ask yourself the question, will it help me determine or fix the amplitudes? Will this symmetry, this is a symmetry, will the symmetry fix the structure of the amplitude? That's the question. The answer is, hopefully it should be yes, otherwise this would be silly to look at. That I can somehow now tell you the whole structure of the amplitude fixed by this symmetry. That's the idea. So let's work that out. It's very simple. That's the thing. You want to use symmetries to fix things. That's the key in physics a lot of the time. So let's just talk about a few more things. So for while fermions, the scaling goes as follows. So for while fermions, the scaling goes T minus 2H, where H is the helicity. So H equals plus or minus a half for while fermions. And the polarization vector is epsilon mu plus minus P Q, also scale as some T minus 2H, except now H is just plus or minus 1 for the polarization vectors. Okay, so under little group scaling, if I have n number of particles, the amplitudes transform nicely just under the weight HI equals minus 2 HI. That's the weight they transform. Oh no, sorry, what am I writing down? The weight they transform with is just minus 2 HI. Okay, based on this power that this guy's raised to for the while fermions. Because this is minus 2 HI. And that's referred to as the weight. Okay, that's just a term, or just, you know. And now obviously this depends on the number of particles you have. Okay. So let's just write down this kind of procedure in general. So if I have an endpoint amplitude now, right, and I'm going to scale it, well, then I'm going to get one term that kind of looks like this. So for the first particle, I might get a bunch of these guys, right, with some helicities. Right? And then for the second term, if I want to scale it, I'm going to get some ti to the minus hi I, right? Because I'm going to be scaling it. Oh no, sorry. This should be to the -1. Sorry. From before, right? And then comma hi. And so now what I'm saying is that the entire amplitude now can be written in the following way. The entire amplitude can be written as ti minus 2hi an 1, oh God, wait a second. Yes. We'll put dots here. So dots, I, hi. Okay. Okay, how does this work? You're going to see in 1 minute how this works. This is the of course, the general expression. We're not European, so it's kind of whatever. Let me know when I can erase. Okay, good. Okay, so let's go back to one of the QED amplitudes we wrote. Okay, so recall that we wrote down this amplitude for QED. We had some A3. We had two fermions and a photon. We had F minus, F bar plus, gamma minus. And we wrote down an amplitude that went E tilde 1 3 squared over 2 3. Okay. That was the basic. Oh no, wait. Should be 1 2. Wait. Yeah, 1 2. Right. So 3 is the momentum corresponding to the photon, right? Then 1 and 2. Okay. Okay, and remember, we have a negative helicity photon. So what does the little group scaling tell us? Little group scaling says that T3 squared will equal T to the -2 times -1, right? Because, wait. Right. Because remember, the weight just goes T to the -2h, right? So T to the -2 times -1 is 2. This is T squared. I have a T squared term, 3 squared term. So it's telling me how it's scaling. Okay. That's all I'm doing right now. Is that okay? So this little group scaling tells me how my amplitude will scale, to what power, based on the helicity of the particle of interest. Is that okay? So that's kind of nice, but it's not really a big deal yet. We want something that's a bit more all-encompassing, just to show you how this one thing will work. But here's the claim. Let me know when I can erase, and then I'll give you my big claim. Okay, here's the claim. Claim. By the way, it's serious when I write down claim, just saying. I've very rarely done it in all of the classes we've had, but claim all massless 3 particle amps are fixed by little group scaling. Okay, so let's work that out. So let's have a 3-particle amplitude ansatz. So let's say A3, right? So we want a 3-particle amplitude times some 1 times H1, 2 times H2, 3 times H3. Okay. And let's say that the ansatz now is some constant times 1, 2, scale to some dimension x. All right, we'll call it 1, 2. Then this guy will be 1, 3, scale to some dimension x, 1, 3. Right? And then this guy will be 2, 3, scale to some dimension x, 2, 3. And this ansatz seems to make sense, right? Because you're just going to have powers raised and lowered, and you'll get some fraction of these guys, right? That's the whole amplitude. Okay, dependent on the helicity. But let's see if we can kind of manipulate this guy. So what does little group scaling say? Well, little group scaling fixes these guys in a very nice way. So little group scaling says that minus 2h1 now will equal x12 plus x13. Okay, that just comes directly from our definition of little group scaling. Right, minus 2h2 will equal x12 plus x23, and minus 2h3 will equal x13 plus x23. Okay, that just comes from the little group scaling. And now we have a nice system of equations that we can solve, right, for various things. So if you solve the system of equations, for example, for x12, we'll say, so x12, if you solve the system of equations, you can do the algebra quick, you'll find that for x12, you get h3 minus h1 minus h2. Get some expression like that. Okay? And similarly, I can solve for x23, x23 and x13 in this way. And wait a second, you should be going, what? I can now write down this whole amplitude based on the helicities or the little group scaling. Okay, that's kind of neat. So let's just write down the full expression after you solve this system. Okay, so that's exercise, what are we up to, 4? Yeah, solve the system. Jenna, you're responsible for telling me all the problems, okay? Solve the system. Okay, for little group scaling. You're gonna have a lot of problems this week because we haven't in a while. And you'll have a few weeks, don't worry. Because I'm done with GR. I'm done with GR. Toss it to the curve, that's it. We have our cosmology notes now. Okay, so now we can just plug in. So let's do that. So this is directly a consequence of little group scaling. Okay, so now, right, so problem 4 will be to verify this. So 1h1, 2h2, 3h3. So this it will be to verify this guy. I'm gonna write these out, don't worry. But in case I forget. So equals some c times 1, 2, h3 minus h1 minus h2. Now I need the other powers. 1, 3, h2 minus h1 minus h3. If this is wrong, don't worry. I'll put in the right expression. Two, 3. h1 minus h2 minus h2. Okay, so something like that. I think it's right. So the helicity structure completely determines the amplitude. That's great. This is a consequence of little group scaling. This is very up to an overall constant, right? So the symmetry fixes the amplitude. This is very similar to conformal field theory. So this is an n equals 3 amplitude. And in conformal field theory, I'll give you a brief description. You actually don't work with scattering amplitudes. You work with something called correlation functions, not the correlation functions from quantum field theory. They're a little different. And if you have 3 particles, it gets a little weird what you actually call them. If you have 3 particles, they're defined now, instead of by these guys, they're defined by things called operators. Again, it's a little more, it's not the regular things you're familiar with. And you find that, let's say you have some expression, this is called an operator product expansion, where 2 of these guys will give you a third one. We'll see what this means. You'll find that the total structure of the operator product expansion is also fixed by a scaling symmetry up to a constant. So this is a very direct analog to that. It's a little different in, but these guys in CFT will be conformal weights. Conformal weights instead of pelicities. Okay, and you will work with them a lot, don't worry. Okay, but this is great. This is great. This is awesome. This is like wonderful. Beautiful. Okay, let's move on. Let's move on. Let's move on. By the way, the paper I'm working on now with Monica Pate and another senior grad student at Harvard, Mina Himwich, is trying to explore a new symmetry for these OPEs and CFT, which is quite interesting. And we're trying to see how it fixes the OPEs. It's very confusing how it's working, but in principle, it's the same kind of game we're trying to play. So just a side thing. Okay, very good. Okay, excellent. Okay, let's go back down to right. So that's little group scaling. That's a very important piece of the puzzle. And let's now go back to gluon amps, okay, for a second. So recall, so if I have a 3 gluon amps, G minus, G minus, G plus, something like that. Schematically, this will be what? G Yang Mills. One, 2 cubed, 1, 3, 2, 3. Schematically. And since these guys have mass dimension 1, so these guys have dimensions of mass. Are you familiar with this notation? If you put something in brackets with a word, it says dimensions. Just, you know. Okay. And this just comes from the interaction term in the Lagrangian. So remember, trace F mu nu has an interaction term that goes A, dA. Just schematically. And so this works because you get 3 over a power of 2. And this just gives you dimensions of mass. Mass to the power of 1, right? Just a quick check. So that's good. Okay, so we've learned that little group scaling fixes the amplitudes. Okay, so here's your other exercise. Here's another exercise. So in gravity, the action goes like what? 1/2 kappa squared integral x square root of minus gr. When we derived the Einstein equations, we ignored this. This is just a little constant term. You can always parameterize g mu nu by some eta mu nu plus some constant kappa h mu nu, right? That's the linearized stuff. And so the problem, compute a 3-point scattering amplitude for gravitons using little group scaling. And it should be really easy now in principle because h for a graviton is just plus or minus 2. Now, if you tried to do this with Feynman rules, you'd have a lot of trouble. But you can do this now with little group scaling. By the way, gravitons are massless. So this is kind of nice anyway in this limit. Everything should cancel out at the end of the day. If we did it the Feynman way anyway. How much time do I have? Okay, good. I'm on schedule. And I'll let you figure out what helicity to use. Okay. That should be easy now. With little group scaling, you can do the check in 5 seconds. Should be very simple. It looks hard. It's very simple. Okay, let's continue. Beautiful. Okay, now let's talk about this helicity stuff. You know, let's get this off our chest now. I think this has gone long enough, but there will be some element of exploration for you. So schematically, I have a Lagrangian and Yang-Mills, and it gives me some interaction term, the gauge fixed one, that goes A dA plus A to the 4th, right? If you just look at the Lagrangian, this is kind of like how the interaction terms work out. And I can write down now any Yang-Mills amplitude in general as the sum of all the diagrams. Sum of all the diagrams. The multiplicative sum of epsilon I dot epsilon j, right? So now I'm just going to have all of those dot products times the multiplicative sum of epsilon I dot kj times the multiplicative sum of ki dot kj. That's kind of like what we're working out all over. So that's all in the numerator, except this. This should be outside the fraction, right? This guy. Times all of the propagator momenta in the denominator, pi squared. All right, so now that's just the basic Yang-Mills structure. So it turns out that for endpoint amplitudes, so this is going to be your next exercise to show this. For any endpoint amplitude, 1 plus, 2 plus, to n plus, with all positive helicity, the amplitude vanishes. Okay. Okay, and it also turns out for any endpoint, if you make one of the gluons negative helicity, it still vanishes. Except for n equals 3, right? Because n equals 3, we had one negative, but it turns out for endpoint, it just vanished. You know how you should show this? You guys are going to hate me for saying this. You should show this with induction. Uh-oh, have we heard of that before? Okay, you should show this with induction, right? You should show that it works for n equals 1, it works for this vanishes for n equals n plus 1, then you add the negative, then you show it works for general case. That's what I want you to try and do here. Sorry, we have to do it. That's what physicists do. Actually, physicists do very backhanded induction proofs, right? It's very funny because like we'll work this out for n equals 3, 4, 5, but then you don't know if it's going to work for 6, right? So you need to use induction. Okay. Okay, turns out the easiest, not the easiest, or the most simple non-trivial endpoint gluon amplitude is an amplitude with 2 negative helicity gluons and everything else positive. That's the simplest non-trivial thing. And in that situation, you'll get something that goes like an, 1 minus, 2 minus, and plus. Everything else is plus, right? So just to hammer that in, we'll put this as 3 plus. Okay. And again, you get something that looks schematically like sum over diagrams. Sum epsilon 2 minus dot epsilon, because 2 has a negative helicity, epsilon I plus, that's going to be a plus. Epsilon I dot KL to, I don't know, to some power, yes, n minus 2, all over the multiplicative sum of pi squared. So these are called, they have a very special name. And the reason they do is because in papers, usually people explore this case because it's the first non-trivial case. Okay, and they're called MHV amplitudes, or maximal helicity violating amplitudes. It's a silly name, but that's what it is. So if you go in the archive, you'll find many, if you type sketch, you'll find many papers with these letters in there, MHV, MHV, MHV. It's because people are exploring the structures of these guys. So it's an easy way to classify it. Because look, I can always add another negative helicity gluon, but then, you know, the extensions are just kind of trivial in most cases. Not all cases, in most cases. Okay. So let's spend the last 10, 15 minutes or so and kind of, I want to motivate something I'm going to discuss next week. I want to begin to motivate how we can use some of these results and extend it to higher point amplitudes. How can I write down just general things? And it turns out there are some theories where I can write down any endpoint amplitude in a few simple expressions. So let's just talk about, it's gonna take me next week to work out everything. I'm just gonna set it up for you a little bit today. So these are called on-shell recursion relations. So we can use these things called on-shell recursion relations to build up higher point amplitudes with lower point information, which is very useful. The most famous on-shell recursion relation is BCFW. For the people who discovered it, BCFW, I'd forget their names, other than W's Witten at the end. So, okay, so what does this mean? So let's just consider a standard momentum in this momentum vector in this space. So again, in this whole spinor helicity, pi squared equals 0, right? Okay. I can go from 1 to 2 to n. And conservation of momentum demands that the sum from I equals 1 to n, p mu I equals 0. Okay. So now consider some complex valued vector. We're going to call it R mu. So this is just some R mu I. So this could be any number of complex valued vectors, right? Just some second thing. Where again, I demand that the sum from I equals 1 to n of all R mu is 0. And I demand that Ri squared is 0. Therefore, I demand that Ri dot Pj is 0. So now, this just seems very silly, but you'll see where we're going with this, as with most things in physics. So now let's define a shifted momenta. So let's define the shifted momenta p hat mu I. And how are we going to define it? Well, it should be pretty intuitive now. We have some p mu I plus we'll call it z r mu I, where z is just some complex number. Okay, that's my shifted momenta. I can shift it by anything now, using this second complex vector, whatever I want to label it as. And of course, the shifted momenta need to be on shell. So p hat mu I, So p hat I squared equals 0. The shifted momenta are on shell, and they also satisfy conservation of momentum. Nothing crazy. I equals 1 to n. P hat I mu 0. The sum of all of them is 0. Does everyone know why I can write conservation of momenta like this? No? Okay, you should ask. So let's just say in a normal Feynman diagram, I have something like this, right? Whatever, right? This is P1, P2, P3, P4. These guys are outgoing, right? So they're going to have minus momenta. These are ingoing. So P1 plus P2 plus will equal minus P3 minus P4. Is that okay? Because they just have to cancel each other out. So if I bring these guys over, well, then I get that everything is 0. The sum of all of them is 0. Is that okay? Okay, so that's just what I mean by conservation of momenta. I'm just writing it a little weird. Okay, very good. Okay, good. So let's take some subset of this shifted momenta. Okay, well, let me just backpedal for a minute. Johnson's, oh, I have plenty of time. Let's just think about this a bit more intuitively, because this seems kind of random. What is a Feynman amplitude made out of? Vertices, internal lines, external lines, right? Propagators. In these spinor helicity amplitudes, what's sort of the only thing that's sort of defining the amplitude? It's the propagator, right? The propagator in the denominator is telling us all the dynamics. So if I can take that propagator and shift the momenta along the real axis in the complex plane, I can, in theory, build up all of the different amplitudes just by shifts of the momenta. That's just the intuitive picture, just so we're not lost in some of this formalism. Okay, so let's take some non-trivial subset. So let's take some little pi. Okay, where I is some element of capital I. You'll see what I mean in a second by this designation. Okay. And big P mu capital I, okay, is a separate object that I just define as the sum of all of these PIs, P mu I. And what am I doing here? I'm taking little p mu I of the shifted momenta, and I'm taking a subset of that. And what I'm planning to do now is create some kind of recursion relation where I keep adding the shifted momenta to the shifted momenta to the shifted momenta to the shifted momenta to build up the whole endpoint amplitude, right? We have to worry about poles, obviously. We're going to talk, we can't ignore the poles or the contours, or we're going to talk about that really, really quickly today. But that's the basic principle. Okay, so let's end with the final kind of comment on this. Okay, so the final comment. So if I have an unshifted momenta, so let's just write that down. If I have an unshifted momenta, then z is just 0, right? Because then that second term drops out. And for unshifted momentas, an equals an of z equals 0, right? That's just unshifted. Okay, so this is unshifted. Let's ignore that. So remember, now we have some shifted amplitude a hat of n of z. This is my shifted amplitude, right? I have a bunch of complex shifts, right, in the momenta. This is holomorphic. This is my condition. Do we know what that means? Oh, okay. It's just a fancy word in complex for analysis for saying something continuous and differentiable. Okay, so this is holomorphic. And we're very lucky at tree level. We're very, very lucky at tree level for the following reason. Everything in the analytic structure is defined by these propagators. 1 over pi squared. Right? And the analytic structure, what do I mean by analytic structure? I should define these things. The analytic structure simply refers to the poles and all of the various crazy complex analysis stuff that can happen. But we're very lucky at tree level because the analytic structure is so simple. We just have one simple pole. There's no branch cuts. There's no, crazy anything. It's just a simple pole. No log cutoffs, nothing. Okay. Right. So how can we write this out now? What's the goal? When we have the shifted amplitude, right, we're going to take the shifted amplitude and we're going to close it off with a contour. It's going to look something like that. Where the residue of this guy is simply, I should write down residue. The residue of this guy is very simple. It's just the unshifted amplitude. That's the residue. And by Cauchy's theorem, I can now write down the shifted amplitude in the following way. So by Cauchy's theorem, I can write this whole guy as a sum of the shifted amplitudes. We'll call that zi. Take out the minus. I don't know why I put a minus there. All the residues at z equals zi. A hat n of z over z. That's the basic idea. So it might be a little confusing with the complex analysis. We can talk about it tomorrow more if it's confusing. But I'll just intuitively comment and then I'll tell you where we're going with this. So the basic principle now is what I'm simply saying to you, what I'm arguing is you can build up any endpoint amplitude in a few ways. You can sort of write down everything like Park-Taylor, right? You can sort of look at patterns, prove things by induction, which is what you're going to do. You're going to show me by induction that you can come up with some generalized expression. That's fine. That's doable. People have done it. Or you can sort of do it backhandedly and say, look, everything in this space is defined by momentas in the propagator. I can simply shift the poles. That's all I'm doing here. That's complex shift means you're shifting the poles, right? Along the real axis. You're just shifting the contour, making a bigger contour. And in principle, it's very simple, where the residue is just the unshifted amplitude. So you start with the residue and then you work out. Very simple. It turns out that I can get a lot more from this actually. So we don't know yet how, I haven't shown you. I will show you soon. Turns out that these recursion relations become a very powerful tool in a lot of different aspects. So whereas Park-Taylor works for Yang-Mills theory, or gauge theory in general, right? And it works. Little group scaling fixes the amplitudes too. We saw that. This works in more areas, in more theories. Which, I don't want to say it's more general, but, kind of. Okay, so does anyone have questions? We learned a lot today. We really covered a lot today in bite-sized things. Does anyone have any questions or?
When we did when you wrote like the claim and when you gave us the problem where we have to verify the system of equations,
Yes.
I didn't get how you got the system of equations. You said it was from the definition of little group scaling. How did you do that?
Right. I'll explain it in the problem set. Okay.
Okay.
I'll guide you through it. I like to guide you through it too in the problems, not just give you the problem. So I'll guide you through it. Okay. Good for bringing it up. But if you want the quick answer, it just comes from this t to the -2h object. So, but I'll guide you through it. Because I want you to work out how to get that system of equations from the 3-particle ansatz. Not just solve it and do the algebra, but actually get the system yourself right. Use it. So that's part of the problem. So I don't want to spoil it here. Okay, but good question. Okay, anything else? Okay, very good. Okay, excellent. So we made a lot of progress. Next week, we're going to do one more day of this. No loops. I'm not going to do loops in this context. And then we're going to do some CFT. Okay. So let me just stop recording.